In this video, we're going to be solving for a roller coaster problem at three different positions using circular motion concepts and calculations. So first of all, if you're approaching a circular motion problem, you're taking a look at the sum of the forces and setting that equal to the mass times the centripetal acceleration, which is mv squared over r. Now, when you're taking a look at the sum of the forces, anything that's going towards the center of the circle would be considered positive, and anything pointing away from the center of the circle would be considered negative. Now, when you take a look at these three different scenarios, only one of them you can clearly see the actual circle. For the rest of them, you sort of have to imagine the circular path that it's taking. So for our first position, your circle is right here, and there is the center of your circle. So we can focus on that certain spot to see if things are centripetal, pointing towards the center of your circle, meaning that they are a positive force, or if they're pointing away from the center of the circle in the radial outward position, and they're a negative force. For our second one, as you can see, the bottom of the curve is going downwards, so the circle would be going more upward in this direction, so the center of your circle is right over here. And then for your last case, the center of your circle is in the center of that loop right there. So let's go ahead and analyze each of these situations. So what you want to do first is go ahead and draw the forces acting on the person in each of those positions first. All right, so now that we've drawn the forces acting on the person in each of the three cases, which is basically just the normal force and the force of gravity, let's analyze one at a time. So at this position over here, where the person is at the top of a hill, you could see the center of our circular path is right there. Our FG is pointing inward towards the center of the circle. So that FG is going to be positive. And then the normal force is pointing in the radial outward position. So you're going to subtract that, and that's going to be a negative value that equals mv squared over r. Now what you can do is you can go ahead and plug in all of those values, and then we can go ahead and find the normal force, and that normal force is going to be the person's apparent weight at that particular position too. So let's go ahead and plug in our values and see what we get. So one value that wasn't written on the screen was the 60 kilogram mass. So went ahead and added that in. So our FG is mg, which is mass times 9.8 minus the normal force, and then m, our v squared, and our r given from the problem. Now, if you add Fn to both sides, it goes to the right side of the formula, and then you subtract this number over here, which is 214.29, from our FG of 588, and we get 373.71 newtons. So this person's apparent weight is less than their actual weight. Their actual weight that they normally feel is 588 newtons, and because they're going towards the top of a hill, they have some inertia heading upwards, so that releases some of the force that they push down into the seat. Therefore, their normal force is less, and they feel a little bit lighter. Now, the big difference between the first situation and the second one is now if you look at the center of your circle, your Fn is pointing inward towards the center of the circle, and your Fg is pointing away. So your Fn is your positive force, and your Fg is your negative force. So for this one, we know that our Fn is our unknown. Our Fg is still 60 times 9.8. We already know that's 588 newtons from our previous problem. And then if we plug in mv squared over r using the v and r provided, then we basically have everything we need. And then our Fn equals, and then we add 588 to this number over here, which is 420, and we get 1008 newtons. Okay, so this one is significantly larger than our first answer because now when you're going downhill, your body's pressing into the seat more. You get more of that equal and opposite force from the normal force. Therefore, you have an apparent weight that is greater than your regular FG of 588, and you feel as if you are 1008 newtons. Now, for our last scenario, now we have a roller coaster where you're upside down in the loop. And as you can see, both of these force vectors are pointing inwards towards the center of the circle. So they're both actually positive. So it's Fn plus Fg. Again, we know Fg is 588 equals mv squared over r. Our m is 60. Our v for this one is 7. And then our velocity, or excuse me, our radius is 5. Okay, turns out once you multiply these two and divide them, you actually get 588. So if you subtract 588 from both sides, your normal force comes out to 0 newtons. So at that particular moment, they feel weightless based on the velocity that they're moving and the radius of the circle. So when performing these circular motion type problems, what you want to do is make sure you sum up all your forces, make sure all the ones that are positive are the ones that are pointing towards the center of the circle. But of course, you have to identify what your circle is. And we did that with our purple dashed line, our orange dashed line, and then just looking at the loop of this actual roller coaster. And then anything that's pointing away from the center of that circle, we make that a negative force. We set that equal to m times our centripetal acceleration of v squared over r, plug in your number values, and then you can go ahead and find your normal force, which is your apparent weight. Or depending on the situation, you can obviously plug in different values to solve for different unknowns. In this video, we're going to be taking a look at two vertical motion problems, an object being swung in a vertical circle, and then secondly, an object or a ball being swung in a horizontal circle. So for our first problem, we're going to solve for the force of tension at two different locations, at the very top and also at the bottom as well. The most important part is to look at the forces acting on the object at the top of the loop and at the bottom of the loop. Now they both have the same forces, which are the force of gravity, pulling it down, and then also the force of tension, pulling it inward towards the center of the circle. And then at the bottom position, we still have the force of gravity, pulling it downwards. And then we have the force of tension, tugging it towards the center of the circle. Now, there is a big difference in setting up each of those formulas to find the correct FT. So let's go ahead and set up our formula for the force of tension, the force of gravity at the top of the circle and at the bottom. Okay, so the big difference is fairly subtle, but is going to change your answer significantly. So let's take a look at the top of the circle. At the top of the circle, we have both of the forces pointing downward. Now remember, when you're working with a circular motion problem, you want to make sure that anything that is centripetal, pointing towards the center of the circle, is considered positive, and then anything pointing away from the center of the circle is considered negative. So at your top position, both of those are pointing inwards towards the center of the circle, so they're both considered positive. Now for the bottom of the circle, we have our FT pulling it towards the center of the circle, but our FG is directly outwards away from the center of the circle. So it's going to be FT minus FG. So it's considering FG is negative. Now, although that is a subtle difference in the look of the formula, which is basically just the sign here, that is going to change our answer significantly. So if we're looking for our FT, we have that as our final unknown. And then for the FG, we're going to do mass times 9.8. Mass is 2 kilograms times 9.8. And that equals the mass times the centripetal acceleration. The centripetal acceleration is always shown by v squared over r. So we have a mass of 2 kilograms And it does not look like we have a velocity, but we can go ahead and use a second formula and do a little substitution. Our velocity is 2 pi r over t. 2 pi times the radius is the circumference of the circle, so it's basically a distance around the circle, and then capital T is the period, the amount of time it takes to complete that circle. So for our velocity, we're going to do that substitution, and we're going to go 2 pi times r, which is just 1 meter exactly, over t. Our period is 2 seconds, divided by 2, and then that entire thing is squared because it's v squared in our original formula. Now let's go back and finish off the rest of it. And so we got the m at the v squared, and then divided by the r comes out to just 1.0. So if we take our velocity, which is basically these two's canceling out, so just a pi left over, times 1 is just pi, so pi squared times 2 divided by 1, and then we're going to get 19.74 newtons. Okay, so all we have to do is we have to do one simple step of algebra, which is subtracting 19.6 from both sides. And then we have our final force of tension value, which is just 0.14 newtons. Okay, you might be asking yourself, why is that value so small? Now, if something is going around in a circle like this, it has some inertia, and then it has that force of gravity holding it down, which is part of its centripetal force. And because it has plenty of centripetal force from the FG, the FT doesn't have to pull it that hard towards the center of the circle. But then once it starts getting pulled downwards, and then FT has to overcome the force of gravity and have that net force to make it go around in a circle, the FT should be a lot larger for our second calculation. So this is our FT at the top. Now, if we want to do our FT for the bottom, it's just going to be a slight change. We don't have to do very much work because we know most of our values. We just know that it's going to be FT again. So FT minus FG. We already know FG is 2 times 9.8. So that's going to be 19.6 equals, and then mv squared over r. We already did the work ahead of time for the mv squared over r, and we know that is 19.74 newtons. So for this one, all we got to do is add our 19.6 to both sides, and then we are done. And then our FT comes out to a significantly larger number of 39.34 newtons. Okay, so once again, your setup in setting up these black formulas over here and over here are going to be the most significant in your setup. And this little minor change in sign from a plus to a minus is going to change our answer a bunch from 0.14 newtons to 39.34 newtons. Now, when you're working out a horizontal circle question, I'm not going to work that out in its entirety, but FG in this case isn't pointing towards the center of your circle or away from the center of your circle, so you don't need to include it with setting up your formula. So if you were to set up a problem like this, basically all you would do is say that FT equals mv squared over r. And that's considering that this is an ideal situation, because if there's an FG pulling it down, it would sag the rope a little bit, and that would be a completely different, more complicated problem that is called a tetherball question in a lot of cases. So if you want to see the video for that, go ahead and click on this link above. But if you're working out an ideal situation where something is swooping around in a horizontal circle, your FT is basically equal to your mv squared over r. And then obviously, depending on what you're solving for, you would do similar type steps and ideas as we did previously with our vertical circle. Out two circular motion problems, one with a carousel swing and then one with a rotor ride. In the first one, we have a radius of 12 meters, a passenger of 50 kilograms. The swing is leaned out at an angle of 30 degrees, and we're going to solve for the velocity that it's traveling around. First of all, you're going to want to analyze the forces acting on it. So let's go ahead and redraw the picture so we have a little bit more space. We have the swing hanging out this way. And we have a force of gravity pulling the person down. And we have the force of tension pulling at a 30-degree angle. Just like we normally would, if we have an angled component, we want to break it up into an x and y component. So we'll call this upward component Ty for tension in the y direction. And then we'll call this component tension in the x direction. Now, if you take a look at each of the forces, you can see that there's only two vertical forces, Ty and Fg. So if you wanted to sum up the forces in the y direction, we would say the sum of the forces in the y direction is Ty minus Fg, and that definitely equals 0 because there's no vertical movement or acceleration. So Ty basically equals Fg. That's going to be a big component into solving the problem because we know force of gravity is mass times 9.8. So if we know the mass is 50 kilograms times 9.8, then we know our Ty value. Our Ty value is going to be 490 newtons. Now, why is that significant? Because we didn't have any part of this triangle. We didn't have the Tx, Ty, or the Ft. And once you have one angle and one part of the triangle, then you go ahead and use some trig to solve for the other parts of the triangle. Now, if I'm looking for a velocity, and it's a circular motion problem, I'm thinking I want to find the velocity one of two ways. I want to use either 2 pi r over t, which is basically a distance over time calculation, where 2 pi r is the circumference of the circle, and then capital T is the period, the amount of time it takes to complete that circle. If I'm taking a look at my values, I do not have any t value, but I do have an r, so it doesn't look like I can solve for the velocity that way. So the second way I'm going to look to is using a centripetal acceleration type calculation, because centripetal acceleration is v squared over r. Now, if I'm taking a look at these forces, the only force I have that's centripetal is Tx. Okay, Tx is the part that's directed towards the center of the circle. So only forces that are directed right towards the center of the circle are considered centripetal. So my net force and my centripetal force is Tx. So that means Tx equals mv squared over r, because the sum of all our forces equals m times a, and the centripetal acceleration is v squared over r, so we got rid of that a and replaced it with v squared over r. Now, if I used a little bit of trig, then I can go ahead and find the x component there. So I can say that the tangent of 30 degrees, so tangent is opposite over adjacent, so the opposite is my ty, and my adjacent is Tx. And then we can go ahead and cross multiply those two. And 490 divided by tangent of 30 degrees is going to give us the x component. (848.71 newtons). Now from there, if I know 848.71 newtons is equal to this side, I know the mass is 50 kilograms from the original values of the problem. I'm looking for v squared, and I do have my radius of 12 meters. So basically what I'm going to do is I'm going to cross multiply these which is 848.71 times 12 divided by 50. And then I'm going to finish off by doing a square root of that entire value because it's v squared. And then once I solve for that velocity, the velocity comes out to 14.27 meters per second. Okay, so our key components of this problem are we want to make sure that we draw a nice force diagram so that we can analyze each of the forces in the x and y direction. In the y direction, our FG is going to be helpful because that's easy to solve for as long as we have the mass, and that gives us part of the triangle. Once you have part of the triangle, then if we wanted to solve for the force of tension, we could because it's the hypotenuse of the triangle, but we want to use that Tx, which is that centripetal force, that force that's pointing towards the center of our circle. If you looked at it up here, it would be pointing in this direction, which is the center of our circle. And then we use a little bit of trig to find that Tx, and then that Tx equals mv squared over r. We're able to do a little bit of algebra, shift some things around, and we got a velocity of 14.27 meters per second. Now, taking a look at our next problem, we have a rotor ride where as it spins around and gains velocity, the person is going to sort of stick to the wall, and then they're going to be slightly off the ground a little bit, and then that force of static friction is going to keep them from sliding down. So the force of static friction has got to be pointing this way to keep them from sliding down the wall as the force of gravity is pulling them down. And then as the wall is pushing against their back, we have a normal force against their back pushing towards the center of the circle. Now, with that being said, we have a few different things we know. We know something similar to what we did last time, which is if we take a look at those vertical forces, the forces in the y direction, we have force of static friction minus Fg equals 0, which means these two are equal to one another. So Fg is 40 times 9.8, which is 392 newtons, and that equals the force of static friction. Now, in the x direction, we just have the normal force. The normal force is going to be our centripetal force because it's the only force pointing towards the center of the circle. So that's going to be our net force that is in the centripetal direction. So that's equal to mv squared over r. Now we're trying to find this radius right here, but I don't seem to have a lot of information here. So I'm going to go ahead and break this down a little bit more because I know when it comes to friction, that includes the normal force. And a little hint I have is I have the coefficient of static friction here. So 392 newtons equals 0.4 times Fn. It always equals mu times Fn, the coefficient of static friction, times the normal force. And then I can go ahead and do a quick calculation to solve for my normal force. And that comes out to 980 newtons. So now I know my centripetal force is 980 newtons. We have a mass of 40 from the original problem, and then that still leaves us with too many unknowns. So what I want to do is I want to use this substitution right here. So velocity equals 2 pi r over t. So I'm squaring it, which is going to make it slightly more complicated. So if I'm squaring everything up from 2 pi r, 2 squared is 4. Pi is squared, r is squared, and then because it's divided by t, the t squared is going to drop down here, and then we still have this r, that's from the original part of the mv squared over r, so one of these r's is then going to cancel out. Okay, so now I'm able to complete the problem because I know that t equals 3 seconds. So I'm going to go ahead and replace this with a 9 because 3 squared equals 9. All right, so what I'm going to do from here is I'm going to do a little bit more cross multiplication. I'm going to take the 9, cross it up and over, and then do 980 times 9. And then I'm going to take the product of all of these, 40 times 4 times pi squared, and then put that in the denominator to divide it. And then I am left with just this radius over here. And then my radius comes out to be 4.47 meters. So the key components for this problem are 1, recognizing your vertical forces, which is your force of static friction minus your Fg equaling 0, because there's no vertical movement or acceleration. And then that way we found the static friction. And then your force of friction is always connected to the normal force, because the force of friction is equal to mu, which was 0.4 times the normal force. And when we found that normal force, that was a big factor in helping us solve for it, because this normal force is this one over here. And the normal force is pointing towards the center of the circle. So it is a centripetal force. It is the net force of the problem. So that's equal to mv squared over r. It looks like it was a little tough to go ahead and find that r value with all those things missing. So we took that velocity and substituted 2 pi r over t. We made sure we squared all those values, did a little bit of algebra, moved some of our variables around by doing some cross multiplication, and then we got a final radius of our ride, which is 4.47 meters. In this video, we're going to be taking a look at a conical pendulum problem, which is similar to the classic tetherball problem as well. Now, the reason why this problem is quite difficult is because they're generally presented with what seems like very little information. For example, this one, we have a mass of 1 kilogram and a rope length of 0.5 meters. Now, if we were to solve for this, there's a lot of different steps we need to get to in order to solve for the tension and the velocity, but at first that seems like not enough information to solve the problem. So the main idea we're looking at is if we take a sum of all of the forces, it's going to equal mv squared over r for anything that's moving in circular motion, which is basically m times a. We have the m here, and then the a is the v squared over r, which is known as the centripetal acceleration. Now, the key to solving this problem is 2 different things, and both of which are creating a triangle and doing some simple trigonometry. So in order to solve a problem like this, the first thing I'm going to do is draw my forces acting on my mass first. So we have the force of gravity straight down, and then we have the force of tension pulling it up on an angle. And that's basically it. Okay, now just like anything else that we have on an angle, we want to make sure we create an x component and then also create a y component as well, which we'll call ftx and fty. So let's go ahead and create 2 different formulas to sum up the forces in the x and y direction and see what we come up from there. All right, so we summed up our forces in the x and y direction, and we came up with 2 formulas. This one equaling 0 because there is no movement or acceleration in the vertical direction. And then along the horizontal axis, we have an imbalance of force because we only have the ftx, and that equals mv squared over r because that is our centripetal force. Now, if we were to look at the top view, if we were to look straight down at this conical pendulum, what it would look like is it would look like a circular path going around the stand or the pole, and then this would be where the pole is as the ball is moving around in a circle. Now, that force of tension would be pointing towards the center. So that is the centripetal force, and anything pointing towards the center of the circle is a positive force. Anything pointing away from the center of the circle would be a negative force. So we just have this positive centripetal force equal to that mv squared over r. Now, again, it still looks like we don't have too much information. And like I said, the key is drawing two triangles, which we will get to shortly. Now, anytime you have your formulas, what you want to do is basically just plug in any number of values you possibly can in order to solve the problem, and then that will actually take you, hopefully, in the direction that you're looking for. So as I'm looking at it now, I really only have a rope of 0.5 meters that doesn't look like it could be directly plugged in anywhere. And then I have the mass of 1 kilogram. That's going to help me find my FG. So my FG is mg, mass times 9.8. Now, if my FG is 1 times 9.8, which is obviously 9.8 newtons, that means our FTY is also 9.8 newtons. So that's going to be pretty significant to us. Our FTY equals 9.8 newtons. If I look at the second part, do I know FTX? No. Do I know the mass? I do know the mass is 1. And then again, we are not very close to a solution there. Now, anytime you have one side of a triangle along with an angle, that's good news because you can solve for all the different parts of the triangle. So this is where the key part comes in, where we can go ahead and draw our two triangles. So first, we're going to draw our force triangle, which looks like this right over here. And we know that the FTY is 9.8 newtons. So if we know that this is 9.8 newtons, we want this FTX because it's part of our formula. So we have the 30-degree angle, and then we have the adjacent side, and we want the opposite side. So we're going to want to use tangent. So the tangent of 30 degrees equals the opposite end, which is the FTX, over the adjacent end, which is the FTY. So we have 9.8 newtons on the bottom. And then we can go ahead and multiply both sides by 9.8 newtons, and then our FTX comes out to 5.66 newtons. So that's good news for us. So we did want this value right over here. Now, the second triangle we're going to set up is actually one of different distances or lengths. So we have a rope length of 0.5 meters. Now, the reason why that's significant is because we want a distance from this triangle. And that distance is the radius. So let's go ahead and draw another triangle off to the side. So we have a 0.5 meter hypotenuse because that is the actual string right there. There's our 30-degree angle still. And then this distance over here is the radius of our circular path. So we want the opposite end, and we have the hypotenuse. So we're going to go ahead and use the sine of 30 degrees, and then that's going to equal the opposite over the hypotenuse. And then again, multiply both sides by 0.5, and then that's going to leave us with the radius of 0.25 meters. All right, so it looks like we have everything we need now because this one is 0.25 meters. So if we wanted to solve for everything we need, we can go ahead and solve for that velocity first. It doesn't matter. We could solve for the tension first or the velocity first. So let's go ahead and solve for the velocity first. We're going to take the 5.66, multiply both sides by 0.25, and then that 1 is not going to be significant mathematically, and then square root both sides, and then that gives us a velocity of 1.14 meters per second. Oh, actually, that's 1.19 meters per second. All right, so we are good with our velocity now. We could have solved for our tension earlier, so let's go ahead and slide back to our force triangle and finish solving that. So we already know that FTY is 9.8, and we know FTX is 5.66 newtons. So we could use either of those two sides in combination with a 30-degree angle in order to get our hypotenuse of the triangle, which is RFT. So let's go ahead and use cosine, but as I said before, it doesn't really matter. Cosine of 30 degrees equals the adjacent side, which is the 9.8 newtons, over the hypotenuse side, which is the FT. And then we're going to go ahead and cross multiply these two. And that would leave us with a final tension of 11.32 newtons. So as I said before, this problem can seem a little intimidating because of the lack of information in it, but once you start setting up values and then plugging them in and then solving for different parts of your two triangles, it will slowly lead you towards your solution, and then you can get your FT and your V. In this video, we're going to be solving a satellite circular motion problem involving the Earth and the Moon, and then we're going to solve for the orbital velocity, and then eventually the period of the Moon. So although there are two specific objects in this case, the Earth and the Moon, this applies to any kind of satellite question. So one main body with something revolving around it. So we have the mass of the Moon, the mass of the Earth, and the R, which is the separation distance between the two. So that R value is actually the separation distance between the center of gravity between the two objects. So R isn't the separation distance just from the surface of the Earth to the surface of the Moon. It's a distance from one center of gravity to the other center of gravity. So in certain cases, you may have to take that into consideration. In this case, our R value is already that distance. Okay, so let's get started. In this case, we have two objects that have an FG, force of gravity, pulling in towards each other. We have the force of gravity of the Earth being pulled this way, and then we have an equal and opposite force on the Moon being pulled in that way. Now, because the Earth is significantly larger in mass, the Moon is the one that seems to get most of the effect as far as the acceleration and velocity, but both of them get the equal force of gravity. So that force of gravity for the Moon is pointing towards the center of its orbit. So that is the centripetal force. So the force of gravity is equal to the centripetal force, and the force of gravity is gmm over r squared. And the centripetal force is mv squared over r. So one of the first things we can do is we can cancel out one of the r's. And the second thing is we can cancel out one of the m's, but you want to be careful which m you are canceling out. Remember, we're focusing on the Moon revolving around the Earth. So we're going to cancel out the m, which is the mass of the Moon. So this m1 is the mass of the Earth. Turns out that the actual mass of the satellite is insignificant. It gets canceled out. So we have our gravitation constant, which is 6.67 times 10 to the negative 11th times the mass of the Earth. And then divided by the radius, and the radius is 3.84 times 10 to the 5th kilometers. So if we convert that, we get 3.84 times 10 to the 8th meters. So that's something to watch out for because the standard unit for mass is kilograms. So that one is in the correct unit. But if it's in kilometers, you definitely want to convert that into meters. Okay, so all of this equals mv squared over r, but the m and the r got canceled out, which is nice. So we only have a v squared over here. So what you're basically doing is you are square rooting this entire side. So after multiplying these two and then dividing it by the r value, we get a velocity of 1018.32. And that's our orbital velocity of our satellite, which is the Moon. Now, second thing we're going to take a look at is we're going to solve for the period of the Moon, so the amount of time it takes to complete its orbit. And the way you do that is you take that velocity and then you set it equal to 2 pi r And we know our R value, so we can just go ahead and plug it in, 3.84 times 10 to the 8th meters over t. Okay, so whenever you're solving for a period, you're going to use the 2 pi r over t formula. 2 pi r is your circumference of your circle, so we're assuming it's uniform circular motion, divided by capital T, the period of that orbit. And if you just cross multiply these two, then you get your answer. And then your capital T, which is your period, comes out to about 2.37 times 10 to the 6th seconds. Okay, and there's our second answer right there. I'm going to go ahead and do one final thing with our period. So the accepted period of a revolution for the moon is 27.3 days. So let's go ahead and take our time and see if that works out. So we have a time of 2.37 times 10 to the 6th seconds. And there are 60 seconds in a minute. And there are 60 minutes in 1 hour. And there are 24 hours in 1 day. So when we do that calculation, basically what I do is I take 2.37 times 10 to the 6th and then divide it by the product of these three numbers combined. If you want, you can divide them each individually, but I usually just take one big numerator, which is just this number because we have all ones across the top, divided by the product of this bottom number right here. And then our period then gets converted into days, and we end up getting 27.43 days, which is pretty close to the accepted value of 27.3 days. But within that calculation over here, we did a little bit of rounding, and there's some other factors that affect the period of the moon that makes it not a uniform circle. But either way, that is how you do the conversion to get the period in days. So to sum things up, when you're doing a satellite problem, you set that force of gravity equal to the centripetal force, and then you will have some cancellations. You'll be able to cancel out the mass of the satellite itself, but the thing that it's revolving around does not get canceled out. One of your radiuses, one of your radii get canceled out, and then you have v squared equals gm over r, and then from there you can solve for a velocity. If you need to find some other specific details, such as the period, then you can set that velocity equal to 2 pi r over t, and then go ahead and solve for that period. So I hope that was helpful in helping you solve for and understand a satellite problem. Thank you for watching and listening.